I'm going to pull up the molecules from this previous exam because I want to talk about, where is it? This one here. Okay, very good. Now, I did not count this wrong because in lecture, I told you that for finding organic bases, all you have to do is look for amine groups. And you have primary amine groups, secondary amine groups, and tertiary amine groups. So a primary amine group would be, let me find my pen, okay, would just be like a R NH2. And so then a proton can nestle up to those lone pairs of that lone pair of electrons on the nitrogen and make that nitrogen positive. This would be ionized now, and it would be aqueous. It would be water soluble. So we got that down. You guys did a fantastic job. Okay, so I tried to do some research on this molecule here, acetaminophen, and I was wanting to make sure that that this was whether this would act as a base or an acid. Okay, naturally you look at this and you say, well, it's a secondary amine, and so it should be a base. And I think it was about maybe all but one student treated this as a base. So I graded it as if it was a base. Okay, but I just thought that that was such a high pKa for this base, and so it turns out that this violates the two things that I told you in class. And so I didn't count off if you treated this as a base, because I told you to treat it like a base essentially in lecture. I said find an organic nitrogen and you're going to have a base, but not in this case. Okay, and why not? Okay, when I said you don't have to worry about alcohols being acidic, well, what's going on with acetaminophen? It's very strange if you think about it, but this is not just a secondary amine. This is an amide. Okay, and so the amide group is this NH carbonyl next to each other. So this thing here, and this is a planar moiety, and this is the amide bond. This is the linkage you have in all amino acids when they make proteins and you know, the polypeptides. They have this linkage in there, and this nitrogen, once it makes an amide, is no longer pH active. Now, why would that be? Okay, I've got everybody's attention. Okay, hopefully, is that this lone pair of electrons is now delocalized. It's delocalized over this whole region. So now those lone pairs are interacting with the oxygen orbitals, and so you got the bonding pi bonding orbitals in this carbonyl, and you've got the anti-bonding orbitals that are interacting with this lone pairs in nitrogen. And so then that lone pair of nitrogen is in a pz orbital that interacts with the pz orbital on this carbon. And so you've got an extended pi cloud, which means that there's no place for that hydrogen, that proton, to find a localized lone pair. And so if the lone pair becomes delocalized, it loses its basicity. Everybody follow that? Okay, so amides are not basic. Another thing too is because this lone pair is pulled into this amide linkage, it pulls electron density from this ring. And so it makes this whole structure planar. And so now the cloud is delocalized all the way onto the ring. And so this whole group is planar, and the electron cloud is delocalized. And what that does is that pulls electrons away from this oxygen and makes this proton very acidic. Well, moderately acidic, okay. Well, actually very acidic. If you get, no, I would say moderately, but, you know, very, it's a very weak acid. Once you get above pH 10, then this proton can come off. But that's still a lower pH than this alcohol would have if you didn't have this electron withdrawing amide group on the other side. Okay, so when doing the scheme, E, let's see if I can, let me try to erase these markings, or maybe I can, I'll just do it. So E is here, and way over here is pH 10, and then it's E minus on this side at high pH, and then HE on this side. And then D, you got that one right. The naproxen was also an acid, so you had HD, and then a pH 4, then you had D minus. So this would change your answers in terms of the liquid-liquid extraction. So instead of counting you wrong, you followed exactly what I told you in lecture. So I went ahead and graded you as if that was correct. But when I did my research on acetaminophen, which I've never asked this particular question before, and so I never ran across this issue of the basicity of amides before. But looking into it, amides are not basic. And in this case, they pull electrons away from that ring and make that proton very slightly acidic. And so once you get above a pH 10, then that proton will come off. And then that anion is stabilized because you can draw resonance structures where this negative charge will move over here onto the ring, either here or there or here or there. I mean, you can distribute that negative charge over many, many atoms. And there's so many resonance structures where that charge hops around on every other carbon. And anytime you can delocalize a negative charge, then it makes it hard for that proton to come back and protonate, because the negative charge is distributed over the whole molecule, not just on one oxygen. So let me pause here. Are there any questions? Just want to make sure I give you an opportunity to respond to this new information. Okay, I did notice that at least one student was calling this codeine. This isn't codeine. Codeine has a methoxy group up here. This is 6-man, so 6-monoacetyl morphine. So this is the morphine molecule, and it's got a single acetyl group in the 6th position. So that's 6-monoacetyl morphine, or 6-man. This was fentanyl. And also I noticed somebody put that this was the acidic nitrogen. But again, if you look at the acetaminophen case, this is an amide right here. Right, so that's an amide, and it's not a base because of the delocalized electrons. What do you see up here? Same thing. So this right here is an amide again. And so those electrons are delocalized across that carbonyl. So this is not the base. This is the base. This is a tertiary amine, and it's going to have those lone pairs. And so this pH or pKa is for the protonation of this nitrogen here. Now the question was, which ones will you have hard time separating? And it was definitely these two, A and B, because they both have the same pKa. So good job, most everybody got that. And I thought it was nice that some people suggested that there may be, even though they both have a pKa of 8, they might have different solubility. And so you may not be able to use a liquid-liquid extraction scheme to separate them based upon pH, but you may be able to, you didn't use this word, but essentially what you would do is you would get them both in the organic phase, and then you would poison that solvent with a second solvent. And that was, so you take both of these molecules and you have them in the organic phase. and say it's, you know, solvent 1, and then you add in solvent 2. And if you knew that, say, the Hansen solubility parameters for these, and if they were different, you could figure out a solvent that one of these preferred that the other one hated. And so when you add in that solvent, it's going to keep one of them in solution and the other one is going to precipitate out. So that's a good way to then, in the organic phase, cause one to crystallize and the other one stay in solution. So that'd be a clever way to separate these. It would still use liquid-liquid extraction and pH, aqueous, organic partitioning to get rid of E and D and C. And then when you have A, B there, then you could maybe use a poison solvent recrystallization, and you could get one to drop out. Then you could filter it away from the other. So good work.